In the last lecture, we were talking about Boolean algebra properties. So we spent a lot of time proving Boolean algebra properties using essentially three different methods. One was perfect induction, or the truth table method, which was essentially the simplest, most straightforward way of proving these Boolean properties, because it's all about plugging and chugging the Boolean variables and then evaluating left hand side and seeing whether right hand side equals the same uh, for those specific input combinations. Then the other two ways were Venn diagrams. We borrowed some concepts from set theory and we looked at how we can use Venn diagrams to represent binary variables in the form of shading and not shading and prove Boolean algebra properties using that. And then the last one was using already proven Boolean algebra properties. How do you prove others? So we looked at all those examples, and you have a homework that you are working on right now related to a lot of those things. And um, in order to get some practice, we are going to attempt to solve these three problems that are laid out on your screen right here. So one is a simplification problem, the second one is the verification problem, and the third one is also a simplification problem. So what I thought was I would go step by step and try to walk you through each one of them. So let's start with the first one. I'm simply going to copy this guy from here. And then I will start working on it right here. So I have a logic expression for f, which is related to three variables, x, y, and z. And the moment I see a lot of complement signs over several terms, I tend towards using Boolean De Morgan's law for this, because I can quickly simplify. So what I'll do is I'll use De Morgan's law first. I will treat this guy as term 1 and then this guy as term 2. So when I simplify the first time, I have x or y complement, and then because x or y, sorry, no, I will not use x, instead I will use a, or b complement is a complement and b complement. So I'm using that property right here. So my a in this case is, sorry, in this case is x nor y. So this will result in a double complement over here. The or sign will become and then I have b complement, which is essentially x nor z double complement. And we know that double negation cancels out, so we get x or y. And right here it is very helpful to kind of put parentheses around these because we are ANDing them. And then I've got x or z. Now you can directly use a property over here, or you can choose to distribute things using FOIL. So you can say x and x, or x and z, or x and y, or y and z. And then x and x will become x. You have x and z here, and you have x and y here, and you have y and z here. And the next step is to recognize that the first three terms have an x in common. So you can pull that out and you get 1 or z or y, or y and z. And this simplifies very nicely because true or anything leads to true. So you can leverage that and then just say x and 1 or yz, which is simply x or y, z. And there's nothing much I can do from here, so this is the simplest form. And the question said this has 3 literals. I don't know if you recognize that, but the result only has 3 literals. What does that mean? That means that the appearance of any variable happens only 3 times. So I'm going to shade those 3 times in different colors, 1 and 2 and 3. So those are the 3 literals in the simplest form, shaded in those 3 colors in the answer. All right, let's do the second one. Verify this equation. All right, so I'm going to copy this. And let's see here, add a page. Now, I can start with left hand side and try to simplify to get my right hand side, or I can do the other way around. And one quick way to actually see what's going on here is to recognize that this function under the complement sign is a exclusive OR operation. And of course, when you complement exclusive OR operation, you get exclusive NOR operation, which is the right hand side. So I know this is true. I just need to prove that. So let's start with my left hand side, because again, I see a big complement sign over the left hand side, which means I can use De Morgan's law and simplify very quickly. So let's do that. Left hand side, I have x and y complement, or x complement and y. The entire thing is complemented, which by the way is also x exclusive or y complement. But that's just to note. We are not going to use that fact for this proof. Let's see. If I keep going, I use De Morgan's law first. I get the first term complemented. The OR sign becomes an AND. And I have the second term over here complemented as well. Next, I have another opportunity to use De Morgan's law for both these product terms. So what I can do is I can use it on the first term here. X becomes X complement. The AND sign becomes OR Y double complement. And AND sign remains as is. And then I have X double complement or Y complement. The next step would be to simplify it down to X double complement becomes X, Y complement remains as is. Next, again, I can use FOIL to kind of expand these out into 4 product terms. So I got X complement and X, or X complement and Y complement, or Y and X, Y and Y complement. And we know that these go to 0. Oh yes, Y and Y complement, X and X complement, those two go to 0. So we are left with X and Y, or X complement and Y complement, which is the right hand side. Also, it is X exclusive NOR Y. Complement of exclusive OR. This is exclusive NOR. All right. questions, guys? All right, so for the third property here, let's just number them. I think I didn't number this guy. So for the third one, I have a pretty long expression, and this might intimidate you. However, things that look scary from the outset are actually very simple because there are lots of things that you can combine. So if I observe this, and also note that there might be multiple ways to simplify a Boolean expression. There is no hard and fast rule saying that only one way has to be followed. As long as you follow the Boolean algebra properties and get to the correct logical answer, no matter which set of steps you follow, it is okay. Meaning, you don't have to use the properties only in one way. There are many ways to do it. Okay, so let's come to this question here. And let's see. Okay, so the first thing I notice is this. There is a x over here, x over there, x over here, x over here. So what do you think is going to happen to all those four terms with an x in them when I pull out that x as a common factor? The first term is going to give me a 1, second term is going to give me a y and z, next one is going to give me a w, and then the next term is going to give me a w complement. And I'm doing that on purpose because I realize that there is going to be a 1 which is going to make the entire term a 1, which means that is simply going to be an x. So from those four product terms, I get just one literal x. Okay. Next, let's see if we can do something about the two terms that are left. So that's one, that's the other term. I think I can pull out a x complement and y as a common factor between these two terms. So I'll do that. X complement and y pulled out as a common factor, and then I have a z or 1 there, which will also become a 1. So all of this goes to a 1, and all of this goes to a 1 as well, which means I can simply go on to write the next step as x from all of the first one. So all of this is kind of yellow, right? And you get x from that, and then from all of this you get x complement and y. Now at this point, I can use 11D, which is to simply write this as x or y. So this is, let me cite this property here because it's slightly unusual to see this. This is 11D. Let's see, that's it. I cannot simplify anymore, so that's my answer there. So it looked quite intimidating at the first, but the moment you kind of focus on pulling out some common factors to simplify, it will tend to be very easy. Questions about this example? Okay, let's see. We talked about the three properties, and then the result has only two literals, and we got x or y, so we took care of that. I think we are done with these sample problems. So let's move on. Oh, in the next few slides, those three problems have been solved, and the properties have been listed out for your reference. And I want you to take a look at that at a different time, just because if you are curious about exactly which properties were used, all of them are cited over here. But the fact that we went through them one time, I'm not going to go through these again. But they're here for your reference. Similarly, for the second problem, which was to verify, and then the last problem, which was a pretty long expression, uh, we did the answer in one way, and there is also another way of doing this, which is cited over here. So take a look at both of these, and these are simply for your reference. We have already done these three examples. Now let's take a look at De Morgan's law, an example of that. And we are going to be focusing on something called pushing bubbles around. So essentially, it is, we are going towards a conversation about NAND and NOR gates, and the use of NAND and NOR gates is very effective because they use fewer number of transistors. We know that from the CMOS transistors discussion, in comparison with AND and OR gates. And the fact that NAND and NOR gates are universal gates. Which means that I can synthesize any logic expression using only NAND gates. So I can convert everything out, similar to example over here. As you can see over here in this example, all the gates are NAND gates. And right now I'm claiming that no matter what kind of logic function you give me, I can synthesize it using only NAND gates. So instead of investing in multiple forms of gates, I will just invest in NAND gates, which on one hand require fewer number of transistors, and on the other hand, I can implement any logic function using them. So I'm just going to invest in NAND gates and make all my logic functionality use NAND functions. Similarly, I could have also done the same job using NOR gates. So all logic expressions can be synthesized using only NOR gates. And it is also called a universal gate for that reason. So these two gates have a lot of advantages, and we are going to look at a few examples where we convert logic gates and logic expressions and logic circuits to NAND-only synthesis or NOR-only synthesis. And all it begins with this. It begins with adding bubbles and canceling bubbles. A bubble signifies what? We know bubble signifies inversion. So let me highlight that here. Bubbles. A bubble signifies inversion or a complement operation, right? A not or a complement operation or a flip operation, no matter what you call it. It is simply changing a 1 to a 0 and 0 to a 1. So let's take a look at this example, and this is simply this is supposed to be fun. This is supposed to be easy. I want you to kind of feel don't get overwhelmed by this discussion. It's supposed to be fun because it's all drawing things and sketching things and pushing bubbles around in a schematic. So here we have a logic circuit. We have two AND gates and one OR gate, right? Now, let me ask you, what do you need to do to this guy? This is the AND. What do you need to do to convert this into NAND? Well, you might say, put a bubble in front of it, right? If you put a bubble in front of that AND gate, like so, you would have converted that to a NAND gate. Okay, so let's do that. So I've simply added a bubble in front of that. And similarly, for the second AND gate, I have added a bubble over there. So I have converted both AND gates to NAND gates by adding a bubble at the output side of them. Now notice I cannot simply add one bubble to a wire. I have to add two. When you add, say you have a arithmetic expression, x plus y, right? Can you simply add 2 to this without changing the value? Oh, by the way, this has nothing to do with this is a separate discussion, right? So let's say f equals, I'm just going to zoom in over here to talk about this. F equals x or y, right? To do some manipulation, let us say you add 2. But you cannot simply add 2 because you have changed f. You have to also subtract 2, right? If you add 2, then you have to subtract 2, then you are fine. So essentially what I mean is you have to cancel out or manipulate it in such a way that f remains unchanged. Similarly, for logic, if you complement things once, you have to complement them again so that logically things don't change. And instead of putting the second bubble, say, right here, we are putting the second bubble at the input of the NOR gate, input of the OR gate. Why are we doing that? Because this turns out is simply a NAND function. How do we know that? We know that because here things are getting complemented first and then going into an OR gate. Things are getting complemented first and then going into an OR gate. What does that equal? Based on De Morgan's law, it equals NAND gate. So that remains as is. This remains as is. And now, because of the use of De Morgan's law, this became that. And as you can see, all of these are NAND gates. So this is a NAND-only synthesis. Did we change anything about the logic? No. This red box over here represents the same logic function as that over there as well as that over there. So logically, we have not changed anything. Questions about this De Morgan's law example of pushing bubbles through. So essentially, what you push bubbles through, you can imagine that these two bubbles that are at the input side of the OR gate get pushed through the OR gate, they come out on the other end while changing the OR to an AND function. Another sort of graphical way to view OR functions. All right, questions here. Now let's take a look at all the functions and their respective De Morgan symbols. So what we have over here is on the left, say for example, we have OR gate, right? So we have OR function right there. The OR gate that we are comfortable with is shown over there on the left. And on the right, its corresponding De Morgan's symbol is listed. Now, how are we able to sketch the one on the right? Well, simply, if you take a look at this symbol is related to the left-hand side of the expression over here. And the claim is that it also equals the right hand side, which is x complement ANDed with y complement, and the entire thing gets complemented. And you can view it like this. These two bubbles get pushed through this AND gate and they come out on the other side, which means that you will have two bubbles on the outside, which will cancel out. And because they were getting pushed through, the AND will become OR, and you get back to your OR gate. Now, using Boolean algebra, also you can take a look at that. So if you consider the left-hand side over here, sorry, the right-hand side over here, let me pull that out over here to say x complement and y complement, the entire thing gets complemented. What is that? Using De Morgan's law, it is simply the OR gate. So we are expressing those symbols or logic functions in their basic form in the left column and in their De Morgan equivalent on the right column here. And you can go through the list, see how you can represent them, verify some of these if you want. So for example, this guy right here, the NAND function equals this. We just did that in the previous example. This is a symbol of a buffer or the identity function. We talked about that a while ago, which is essentially an inverter followed by another inverter. So two bubbles. Now this is a symbol of one inverter, but you are inverting the symbol after it goes through the triangle. Over here, the input is getting flipped. They are both equivalent symbols. So I would encourage you guys to take a look at this, see whether you are able to validate some of this. We have already validated a couple of them using symbols, the concept of pushing bubbles through, and the concept of Boolean algebra. At least for the first one, we did all of them. All right, let's add one more slide here. And the next thing I want to do is show you a NOT functionality. So that's a NOT gate or the inverter. So I'm going to ask a question over here. Can I synthesize NOT using NAND? So my claim was that I can synthesize anything using NAND. So I should be able to synthesize NOT using NAND. So can I do that? Well, I can do that by doing this. I know x and x is x. That's my Boolean algebra property. So if I complement both sides, what do I have? I have x NAND x equals x complement, which means a NAND function with same inputs is the same as a NOT function. So using symbols, I can say a NOT gate with x as the input and x complement as the output is equivalent to a NAND gate with both inputs tied together. And I can similarly do the same thing for NOR. So let me copy this entire thing and paste it over here and write the equivalent statements for NOR. This becomes NOR. All right. So this becomes OR. X OR X is X, which implies X OR X complement is X complement. On the right, I have NOT. On the left, I have NOR, which means my NOT gate is simply a NOR gate with two inputs, both the inputs tied together. Similarly, you can do the same thing for other gates. So let's see. Let me try to do this. Let me say and, right? And I will put a line in the middle. On the left, I will have, let's say, NAND only. And then on the right, I have NOR only. So my goal is to synthesize AND function using only NAND gates and only NOR gates. So let me start with NAND because it's quite easy. I start with AND symbol. That's what I have. Now, if I want to convert that to NAND, what do I need to do? Well, I need to add a bubble at the output. But can I add only one bubble? Probably not. I have to add two bubbles. So the second bubble I will add is essentially a NOT gate. So now they are okay. Next, I will say this is my NAND, and the next one, which is the NOT, is essentially another NAND with both inputs tied together. We have already seen that. That's a NOT gate. So I've synthesized an AND function only using NAND gates as shown. Similarly for NOR, let us see if we can get AND function using NOR only gates. I start with NOR, right? So let me say I have this guy. Sorry, I need AND. I start with AND, then I have to transition to NOR only. So I have AND. Now what do I need to do in order to make this into NOR? Do I have to add bubble at the output? No, I don't. If I add bubble at the output, then essentially I am going towards NAND. So I have to add bubbles at the input side. But I cannot add bubbles one at a time. I have to add bubbles two at a time. Same AND gate, but I have added bubbles, two of them at a time on the two inputs. What is this guy? This is input complement and input complement equals X NOR Y. That's De Morgan's law. So that's a NOR gate. And I also know that I can sketch NOR gates for NOT. So I have NOT gate there. I have another NOT gate there. And then both of these go into another NOR. So I have now, so let's see, this is highlighted in yellow. All of that is represented this way. this is highlighted in blue, all of that is represented this way, and then you of course have the NOR using the De Morgan's law. So we have essentially synthesized an AND function using only NAND gates on the left, using only NOR gates on the right. Questions about this? What is crucial over here is for you to think about whether you are going to add bubbles at the output side or at the input side. And also, while you are adding bubbles, you have to be careful that you cannot just simply add one bubble, because that will complement the function. You have to add two so that double negation cancels out. As long as you keep track of those two things, you can convert any logic function into NAND-only and NOR-only synthesis. All right, friends, let's move on here. Now that we have a solid understanding about pushing bubbles through and converting things to NAND-only synthesis, and in fact, we also looked at NOR-only synthesis as well. But over here, we are going to try to prove that X exclusive OR Y, which is indicated by that logic function there, which is simply X complement and Y. This is complemented and X and Y complemented, and there's a complement there. So you're essentially trying to prove that exclusive OR operation is the same as all of that. So you can prove this using Boolean algebra, using De Morgan's law very quickly. But we can also prove this by pushing bubbles through, and we'll take a look at that in just a bit. So first we start with the AND OR gate diagram for exclusive OR. So what's an AND OR gate diagram? Well, the AND OR gate diagram is first have a set of AND gates. I'm going to highlight them in yellow here. So that's sort of the first level. And I will point out the level by indicating things vertically. Right. All of those are getting executed, or all of those logic functions are being performed at the same time. Then, so that's the AND level, and then followed by the OR level. So for OR, I have this guy, which is the second level. So you can call this level 1, and this you can call that level 2. Meaning all the logic gates in level 1 are going to perform their operation at the same time. All the logic functions in the second level are going to perform their operations at the same time, and so on. In this case, we only have one gate in level 2. All right, let's see. Is this diagram a correct representation of exclusive OR? Let us try to check. If you have inputs X and Y, at the first gate, what do you have? You have X complement, right? Because here you have X complement, and here you have Y, and they're getting ANDed. So you have that on the first, and then over here you have Y complement there, and you have X there, so you have X and Y complement there. And then you have a OR operation over there, which means you have X or X and Y there. Inequality detector. This is consistent with the exclusive OR truth table. So for now, so we start with exclusive OR operation. And so far, I hope that you agree that this is exclusive OR. Next, we are going to start pushing bubbles through. So before we do that, let me ask you where you are going to add those bubbles. So let me highlight those in pink. where am I going to add bubbles? For the AND gates, I'm going to try to add bubbles at the output here so that I can convert them into NAND. And for the OR, I have to add bubbles at the input side. And the good news is that those bubbles will cancel out, right? So now let's take a look at those steps. This is the first diagram over here is from before. We have added a bubble there and there and there and there as we discussed, and all of those became NAND functions. I'm going to highlight those NAND functions here, here, and here. This diagram can be represented using the logic functions by using this. So that's essentially how you push bubbles through and convert to a NAND-only synthesis. Questions about this example? All right, looks like you guys are comfortable with this. Let's talk about combinational analysis. Well, I just introduced a new term here, combinational. So what does combinational mean? Combinational analysis. Well, these are a classification of logic circuits in which there is no memory. So let me write that, no memory. Okay. What is the opposite of combinational analysis or combinational circuits? The opposite, or the counterpart, I should say, is sequential circuits or sequential analysis. Sequential circuits have memory in them, and the second half of our course will deal with sequential elements. For the first half, we are going to only look at combinational analysis, which don't have any memory in them. How do you define combinational analysis? Where is the word combination coming from? This is how. So for combinational, the definition is output or outputs, there might be many, depend on the combination of current inputs. So you tell me the combination of the inputs. What are they? In this case, tell me the values of x, y, and z, whether they are 0 or 1, and I will tell you what is f. So the output over here, in this case, our output is f, but there could be many, depend on the combination of inputs. Inputs are x, y, and z. Another way of looking at it is things are only moving from left to right. There is no feedback, there is no memory, there is no wire coming like this, right? So that's combinational analysis, and these are by nature simpler than sequential elements, and are easy to understand because they only flow in one direction, one way, left to right. Now, the question, so that's as far as combinational is concerned. Let's talk about the question on the slide. What is its functionality? Now, if I said, I am giving you a circuit, tell me what this circuit does. One way to do this, which is kind of not a very elegant way of doing this, is to make a truth table. X, Y, Z. I will evaluate X, Y, Z because there are 3 inputs. I'm going to evaluate this for 0, 0, 0, track all those inputs all the way here to find out what is f, and then enter here. And then do this for 0, 0, 1. right? And then track it down, and then track it down for 8 of those different combinations. That is one way of doing it. And once you have the truth table, you can go to a logic expression, you can draw a schematic, you can use Boolean algebra to simplify that expression. So you can do all of those things, but you know, this step involves writing out a truth table in the first attempt, which involves plugging in 3 values 8 different times, which is sort of tedious and unnecessary, it turns out. Another problem with this is, what if you have 4 inputs? What if you have 5 inputs? Are you going to keep substituting 16 values, 4 values 16 times, or 5 values 32 times? Are you going to keep expanding exponentially? Well, that's not a solution, right? That's not a sustainable solution, at least. So what we are going to do instead is to work using logic expressions. So let's do that. This involves tracking down the terms as variables. So what is that? At that point, what would you get? Well, at that point, the logic expression, the intermediate logic expression would be x or y complement, because this is y complement and that is x, going through an OR gate. Next, what do you have here? You have z over there. This is the AND function. So what do you have here? You have z ANDed with x or y complement. What do you have here? You have x complement there, you have y there, you have z complement there. So in this case, you have x complement and y and z complement. This is AND, this is OR, and f would simply be the sum of these two terms. So x complement and y and z complement, or z and x or y. That's it. Very straightforward. Now, you know, it hardly took me any time to do this, and I have gotten the logic expression for this. Now, can I use this logic expression to fill out a truth table? Yeah, very quickly. So let me show you how to do that. So what I'll do is I'll simply copy the logic expression over here, and I will show you how you can fill out a truth table quite comfortably. This was the f from before. That was the expression. I'm going to use a little bit of Boolean algebra here. I've got x complement and y and z complement there, or x and z, or y complement and z here. Next, I'm going to try to make this into a canonical form. I'm going to talk about what canonical form is in just a bit, but I'm going to try to force the missing literal. Force missing literal. And while I'm doing this, I cannot change the logic itself. I have to do this in a add 2 subtract 2 kind of manner. I have to cancel out what I did. All right, so let's do that. X, y, z. The first term already has all the 3 input literals. This logic function has x, y, z as inputs. The first term already has those 3 input literals represented. So that is already a canonical form. It's not missing any literal. The second one is missing y. So I'm going to force y on it. Notice I did not change the logic here. And then the last one is missing x. Again, I did not change the logic there. Next, I'm going to expand this into x, y, z, x, y complement z, x, y complement z, x complement y complement z. Done. Are there any terms that are identical? Let's see. Yes, these two are the same. So I only need to write one. X or x is x. So I only need one. So I'm just simply going to maybe gray out or shade out this term. I only need one of them. Where do they lie in the truth table? X, Y, Z, F. Let's see here. 0, 0, 0, 1, 0, 1, 0, 1, 0, 1, 2 zeros, 2 ones, 2 zeros, 2 ones, 4 zeros, and 4 ones. This term is corresponding to a particular input combination. What is that combination? X has to be 0, Y has to be 1, and Z has to be 0. What is that? That is right here. So that is a 1 there. Next, all three are 1. Next, 1, 0, 1. Next, 0, 0, 1. All the others are going to be having a value of 0. That fills out the truth table. So this is a technique that we will see later, how to essentially manipulate an expression and represent it in canonical form. This is what is canonical form here. This is a canonical form. This is essentially a sum of products. Sum of products. Each term over here is a product term. We are actually summing them all the different products, and this is a canonical form because each product term has all the input literals represented. In short, we write this as CSoP, Canonical Sum of Products, which is this guy right here. All of this. And of course, there will be a canonical products of sum as well. And we'll take a look at all those possibilities in just a bit. Okay, so that was a little bit of a discussion here. And then let's talk about those new terminologies in a little bit more detail, in a more organized manner. So the standard representations of logic functions, you can use a product term, you can use sum of products expressions, you can use a sum term, you can use products of sums, a normal term, and there is also a min term and a max term. Let's take a look at what a product term is. So what I'll do is, a product term is going to have in variables that are getting ANDed together, right? So I will take an example here. Actually, I will just take an example from this itself, because this has some product terms. Now, if you look at this expression here for f, how many product terms are there in this? Well, this is the first product term, This is the second product term, and this is the third product term. So a product term is a term in a sum of products expression which involves the AND operation on certain input literals. So you can see that there is an AND happening between two of them, AND happening between two of them, AND happening between three of them. And in fact, even if you had just like plus X, even that would be considered as a product term because it is getting X and 1. So all of those are product terms. That's a definition of product term. Input literals getting ANDed together. How about a sum of product expression? If you have product terms and if you do a sum of those products, you get a sum of products expression. In short, we write that as sum of products, SOP. How about a sum term? An example of a sum term can be, let's see, X or Y complement. It could be Y or Z. It could be simply X complement, right? Because it is or 0. So X complement. So all of those are sum terms. Now, what is the difference between product term and a sum term? Product term involves ANDing of input literals. Sum term involves ORing of input literals, OR gate between input literals. Those input literals could be in true form or complemented form. So it could be X or X complement. Those input literals can be in either one of those forms, true form or complemented form. However, there will be a sum operation or operation for each of those terms. Now let's talk about a product of sums expression. What is a product of sum expression? POS in short. Can I write a POS using, I will use a different G equals. I will use the sum terms that I defined earlier. So I will say X or Y complement ANDed with Y or Z ANDed with X complement. So I have got product of sums. Where is the product? The product is happening here and here. Of sums, where are the sums? And the sum terms? Here, here, and here. So you've got products of sums expression. Now the next three things are related to each of those terms and their properties. So a normal, I will come back to normal term at the end. I will talk about minterm first. A minterm is defined as a product term in which all input literals are represented in true or complemented forms. Now, to talk a little bit more about this, let me erase these highlights. I want you guys to observe that expression right there at the top. Are there any min terms in that expression? Think about that. And I will also have to tell you that f depends on 3 inputs, right? So I will say f is a function of x comma y comma z equals followed by all that expression. So now can you tell me if there are any minterms in that expression? And if so, how many are there? How many minterms are there in that expression? You can write your answer in the chat box. One is absolutely correct. So here the keyword is all input literals have to be represented. And it's a product term. So the only product term, there are several product terms, right? There is x complement and y and z complement. The next product term is x and z. The third product is x complement and z. The fourth product term is simply x. But is there a product term in which all three x, y, and z are represented? Yes. Which one is it? It is only the first term. Only that term is a minterm here, because that's the only one in which x, y, and z are represented. X and z are represented in their complemented forms, and y is represented in its true form. That's your minterm, indicated by small m. We'll talk more about that in just a bit. Next, a max term. Max term, the definition is pretty similar. So what I'll do is I will copy the definition here and I will paste it right here for max term. And now it is going to become a sum term. That's the only difference. And that will be a max term definition. Now, how about this? G is a function of x comma y comma z. How many max terms are there in that expression? Are there any max terms in that expression? You guys are absolutely right. No max terms in that expression, because the first sum term doesn't have z, the second sum term doesn't have x, the third sum term doesn't have y and z. So no max terms in that one. A max term will be something like this, right? If it's a function of 3 variables x, y, z, a max term might be that, right? Or it could be that, and so on. Max terms are represented by capital M. Min terms are represented by small m. Now, I had left out normal term. In a certain expression, like the first one, right, in the red box, the first product term is a min term. However, the second and the third and the fourth terms are normal terms. So a term, a sum term or a product term that is not a min term or a max term is a normal term. So it goes for both sum and product. Right. So not a minterm or maxterm. So these are normal terms, these are normal terms, right? All right, so I think we have talked about this enough. Let us actually define a couple more things. Let's talk about canonical sum of products. This is canonical sum of products. A canonical sum of products expression is a sum of minterms. Canonical product of sums. It is going to be a product of maxterms. We have defined minterms earlier. We have defined maxterms earlier. We know what sum is. It is a simple OR operation. We know what a product is. It's an AND operation. So a sum of minterms is a canonical sum of products expression, and a product of maxterms is a canonical products of sum expression. So you can take these two definitions, and if you had applied it to this discussion here, we said this was canonical sum of products, and if you look at this, you have 1, 2, 3, 4 unique minterms in that, and it is a sum of those 4 unique minterms, and that's why we called it a canonical sum of products expression. Now you can clearly see that each row in this truth table maps to each unique minterm, and minterms are the places where essentially we have a 1 in the truth table for logic function f. So we should be able to do this in a very systematic manner by perhaps numbering each row in the truth table. That's exactly what we are going to do next. So instead of writing this complicated expression here, we are going to write it as a sum of minterms by essentially saying sum of those 4 entries in the truth table, indexed or referred to as their row numbers. That's where we are going next. So let's try to identify those minterms and maxterms for each particular row. So we are going to index each entry in a 3-input truth table using row numbers. Those row numbers are from 0 to 7. So 8 of them for a 3-input case. Then it will be 0 to 15 for a 4-input case, 0 to 1, 0 and 1 for the 1-input case, 0 to 3 for a 2-input case, and so on. You get the idea. Now for each row, say row 0, what do you have? The first row in the truth table is x is 0, y is 0, z is 0. So the function f is evaluated with x is 0, y is 0, and z is 0 in mind. In our particular f, what did we get? We got a 0 there for the f when we evaluated using those 3. So we had put a 0 for that entry there. In our example, not in general, in our example. That was corresponding to this particular minterm. X complement and Y complement and Z complement. If X is 0, Y is 0, Z is 0, then X complement is 1, Y complement is 1, Z complement is 1, and only then the ANDing of those three things will lead to 1. So that particular entry will correspond to minterm 0. So I can simply write that as small m subscript 0. The, the corresponding max term is going to be X or Y or Z. So this is trying to make things 0. Only when X is 0, Y is 0, Z is 0 is the max term X or Y or Z 0. So I'm going to indicate that as capital M subscript 0. Similarly, I go down this list. X, we know how many combinations are we going to have for XYZ. It is going to go from 0, 0, 0 all the way to 1, 1, 1. In the next column for output F, I am evaluating the F with X and Y and Z substituted for each of those particular rows, followed by those corresponding minterms and max terms. We can take a look at, say, 3, row 3. We'll try to take a look at row 3 here. So for row 3, you have X is 0, Y is 0, Y is 1, and Z is 1. You evaluate some logic function, F, by substituting those three input combinations, 0, 1, 1. And you might get a 1, you might get a 0, whatever it is, you will fill it up. And its corresponding minterm would be X is 0, Y is 1, Z is 1. So X complement and Y and Z, indicated as minterm 3. You see, I'm referring to them using their row numbers as opposed to the entire term X complement and Y and Z. Next, the corresponding max term is exactly the flipped operation, flipped X or Y complement or Z complement. That's my max term 3. In general, you can say this. Minterm K is equal to max term K complement. And it works the other way also, right? Like if you complement this guy, you get that. And you can, take any two combinations. Like for example, you can take these two. You can apply a complement to one of them and use De Morgan's law to get the other. So you can quickly prove that identity. The complement of a minterm is a max term. The complement of a max term is a minterm. K is indicating, over here, K is indicating the row numbers. So row 0, row 1, it satisfies for all of them. All right, so I hope that was helpful. Now let's take a look at representing the logic functions using their canonical forms. And we have already talked about this. The canonical forms are going to be sum of minterms or product of max terms. And they both rely on the fact that truth tables are going to uniquely define the Boolean functions completely. There are two standard forms like we talked about, canonical sum of products, canonical product of sum, that can be derived from the truth table. So we'll do some exercises here. We have a sample truth table A, B, C are the inputs. They are laid out as 0, 0, 0 all the way to 1, 1, 1. We know how to write those entries on the input side of the truth table. And for some arbitrary logic function, we have been given that those outputs f are 0, 0, 0, 1, 1, 1, 1, 1. And our goal is to write the sum of products expression for f. So what do? We are doing sum of products, which means we are doing sum of minterms. So we are going to look at minterms. Where are the minterms? Minterms are product terms. Essentially, those product terms are trying to make the logic expression go to 1. So we are not going to focus on the entire f. We are only going to focus where are they 1. They are 1 in these 5 locations. For each of them, you can write a particular minterm. So what is the first minterm? The first minterm is when A is 0 and B is 1 and C is 1. That can be written as A complement and B and C. Similarly, you can write down the other the other 4 terms, each corresponding to a 1 in the truth table. That is for f. I can write f in other forms as well. Let me write f in a slightly different form, in a more compact form. F is the summation of, let me write it this way first. F is minterm, what is that? Row number 0, 1, 2, 3, 4, 5, 6, 7. Those are the row numbers. So row number 3 plus minterm row number 4, minterm 5 plus minterm 6 plus minterm 7. That is one way of writing the function as well. Another, is there something that I'm missing here? Can you guys tell me what information I'm missing in this expression? I purposefully left out one thing that is missing in that expression. What do you what crucial information did I miss there? Anyone? All right, let me ask you a leading question here. Do those numbers 3, 4, 5, 6, 7 mean anything if I switched around the inputs, the sequence of the inputs? So if I were to write the input sequence as C, A, B, will these numbers stay the same? They will not. So I cannot just index the rows as 3, 4, 5, 6, 7 without informing you about the order of the inputs. In this, those specific numbers are the minterms when the order of the inputs is A is the most significant, C is the least significant, or it's going from left to right as A, B, C. So I need to include that as part of my expression. So instead of writing simply f equals all of that, I need to say f of A, comma B, comma C in that order equals that. Now it is making sense. I didn't have to do it over here because I wrote the complete expression in this case. So this was complete. So I didn't need that information over there. But when I index them or refer to each minterm using their row numbers, then I need to explicitly indicate the order of the inputs. If I don't, then those numbers don't mean anything. All right, so let me write this expression in a few other forms. a summation of minterms 3, 4, 5, 6, 7. And we have other forms as well, as you can see over here. A very, very compact form is shown here, which is a summation sign, which tells you that it is a sum of products. The order of the inputs is A followed by B or followed by C. And inside the parentheses, you have the minterms. So that's how you can read this as minterm 3 plus minterm 4, minterm 5, the thing that we just wrote. Also note the order of the inputs explicitly written. Without that, those minterm row numbers don't make any sense. All right, let's go back here. So that is the shorthand notation, right? That's the shorthand notation. So instead of writing the entire expression this way, you just write the shorthand by referring to each product term as a number. All right, let's move on here to F complement. Now, F complement is essentially the complement of F, right? So you're taking F and making into F complement. When you do that, you are switching all the zeros to ones here, 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 and then ones to zeros at all the other places. And if you write F complement expression as a sum of product expression, you will only need to focus on three things here, the places where it is 1. So you get 1, 2, and 3. Those three as the product terms for F complement. They can also be written in the shorthand form. So for example, I would say F complement as a function of ABC equals sum of minterms 0, 1, and 2. Because 0, 1, and 2 are the rows in which F complement is 1. Can also be written over here in a slightly different way. Summation, the subscript is A, B, C, indicating the order of the inputs, followed by 0, 1, and 2, indicating the minterms that are getting summed up. This is for F complement. Those are your sum of products, or this is essentially canonical sum of product forms. In this case, it is canonical because we are dealing with minterms here. Let's take a look at the product of sum expression for the same truth table. A, B, C are the three inputs. F is written the same way, so it's the same arbitrarily chosen output here. The corresponding complement of the function is also written up, so this is exactly the same as before. But now, because we are focusing on product of sums, we will be dealing with max terms and the corresponding zeros in the truth table. So where are the zeros? For F, they are located in row 0, row 1, and row 2. So I can write the expression for F as a product of sum expression as A or B or C, that corresponds to that. A or B or C complement, which corresponds to that. And then ANDed with A or B complement or C, which corresponds to that. Those are the three locations where it is 0 in the truth table. Can be written in a shorthand form or a compact manner as, in this case, we are doing a product. So pi. What is the order of the inputs? A, B, C. What are the rows that are getting max terms? 0, 1, and 2. That's for F. Similarly, for f complement, we are going to say the zeros are here, 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 which is indicated by product, order of the inputs, row numbers where it is 0, 3, 4, 5, 6, 7. So we have the complete expression listed and also the shorthand form listed over here for canonical products of sum expressions, because we are all dealing with max terms over here. Now, I hope you notice that whatever goes in the product of sum expression for f 0, 1, 2, the complement of that goes in f complement 3, 4, 5, 6, 7. Similarly, when we were doing the sum of product, if 3, 4, 5, 6, 7 went as minterms for f, 0, 1, 2 were minterms for f complement. And in fact, if you attach these two together, the sum of product and products of sum, whatever you had in terms of minterms for f complement, those were the same max terms for f, those same numbers. So we can summarize all these observations into, well, this is kind of the same thing listed again, summarized over here. We can summarize those things by talking about complementary relationships between minterms and max terms. So both the functions are listed here. On the top we have f, on the bottom we have f complement. The order of the inputs is listed as A, B, C. So A is the leftmost, C is the rightmost. And their sum of product expressions, I'm going to highlight the sum of product expressions in, say, red boxes. Shorthand, shorthand. Their corresponding max terms or canonical products of sum expression in shorthand is listed over there as well. Now, if you notice the complementary behavior, if 3, 4, 5, 6, 7 goes here, 0, 1, 2 goes over there. So there is a complementary relationship between SOP and POS. And it works the same way for F complement. Sum of product expression, wherever the ones are, the others will have a 0. Now, complementary relationship between minterms and max terms, that's kind of like the horizontal complementary relationship, but we also observe that there is a complementary relationships vertically as well. So we can list that out, showing this, the complementary relationship between f and f complement. So whatever goes here in terms of minterm numbers 3, 4, 5, 6, 7, the remaining goes over here 0, 1, 2. And all of this is 8 numbers because we are dealing with a 3 input case in this one. The number of them may increase to 16 in total, so 0 to 15 and so on. All right, questions about canonical forms, product terms, how to represent a truth table in a shorthand manner, in a complete expression, and so on. All right, let's move on now. Now we have talked about cases where we have an output of 0, an output of 1, but there could be also an output for which the designer, the user, doesn't care whether it is 0 or 1, on or off. Those particular conditions are called don't care conditions. Those are also called incomplete functions. So don't cares are when the outputs associated with certain input conditions can be ignored. So for example, if you were designing an elevator controller
and the building for which you are designing an elevator controller has, say, 40 floors, right? So 40 floors in the building. How many bits would you need to identify each floor? How many bits would you need to identify each floor? Use the chat box, please. So there is an answer of 6. There's also an answer of 7. So here, 2 raised to 5 is 32. 2 raised to 6 is 64. Yes, so we would at least need 6 bits to identify 40 floors, because with 5 bits you can identify 32 floors. So we will need one more. But when you go to 6 bits, you can identify 64 floors, but you only have 40 floors. So what do you do with the remaining 24 floors? The 24 different combinations. What do you do there? Those are ignored. Those are don't cares. And because these are don't cares, these inputs essentially cannot happen, right? Nobody is going to go into an elevator which has 40 floors and want to go to the 41st floor. There's nothing like that. So it cannot happen in a good design. So we can use these don't care situations to actually simplify the logic expressions to a great extent, and we will take a look at that in the next lecture. But those don't care situations are the ones in which the inputs can be ignored. So instead of writing a 0 or a 1, we are going to indicate don't cares by using X. Now let's take an example in which you use binary codes for decimals. BCD, and keep incrementing by 1. How many bits would you need to code decimal numbers? How many decimal numbers or decimal symbols do we have? We have 10 symbols in decimal numbers, 0 through 9. So how many bits would you need to identify 10 different symbols? Well, you would need 4 bits to identify 10 different symbols. But this is only 0 to 9. With 4 bits, you can go 16 combinations. So what happens to the other 6? Those are don't cares. And as you can see here, we are describing that as don't cares for what. So decimal numbers 0 through 9 are being captured in BCD, binary coded decimal, as 000 all the way to 1001. We know that from the first set of lectures that 0 through 9 can be captured in BCD code that way. After that, if you keep incrementing by 1, what you have is decimal 10, 11, 12, 13, 14, 15, which cannot happen. So it's not a valid input, indicated as an X in the output. Now let's do this. Let's write up a truth table here. Let's do a good example. So what I'll do is I will start off with a truth table. Let us stick to M and P. And my output is, say, Q. And I have 0, 0, 0, 1, 0, 1, 0, 1, 0, 1. 2 zeros, 2 ones, 2 zeros, 2 ones, 4 zeros, and 4 ones. And then in the output side, let me use some of them as zeros, and then couple of them as ones, and then I will also use don't cares. So I've arbitrarily sketched up this queue as some truth table with some zeros and some ones and some don't cares in the output. Now my goal is to write Q in various forms. So how can I write Q in a complete expression? CSoP. Complete expression CSoP. Where are the ones? In the row 1 and row 3. So that would be M complement N complement, let's see, P, or there is M complement N and P. So that's a canonical sum of product expression right there. Can I write that in terms of a shorthand notation? The order of the inputs followed by the row numbers. What are the row numbers here? I've got row 1 and row 3, but I also have to say that I don't care about input combinations for what is that, 6 and 7. So those three correspond to 4, 6, and 7. And these two guys correspond to that and that. Similarly, I can do this for the other one, CSoP, CPoS. What do I have here? Q equals, let's write the expression M or N or P. That's for the first 0, ANDed with M or N complement or P. That's for the next 0, and then ANDed with the last one is what? M complement N P complement. That's for the last 0. This can be expressed in shorthand as pi order of the inputs. This is going to be row 0, 2, then I have 5, and I have also don't cares at 4, 5, 4, 6, 7. Because these don't cares can go either way, 0 or 1, I have to include that as don't cares for both the CSoP or CPoS. All right. Questions about this example? For the sake of completeness, I will also just indicate the row numbers here. All right. Let us keep moving here. Actually, let me stop the recording.